One of my favorite New Yorker cartoons has two dogs walking slowly down the street by themselves. One dog turns to the other and complains, "It's always sit, stay, heel, never think, innovate, be yourself." Here at Caltech, we always expect you to think and to innovate. We want you to take advantage of opportunities, curricular and co-curricular, that let you tread new pathways and be yourself. A warm welcome to Caltech. You are now part of one of the great universities of the world. We return to campus at a miraculous time to do science and engineering. New vistas on the universe have opened with gravitational wave detection. The entanglement frontier promises a new revolution in quantum information and matter. Insights into the fundamental biology, chemistry, and engineering of the human body promise to relieve suffering and prolong life. Machine learning combined with human insight has the potential to discern patterns that can transform the disciplines. Breakthroughs in renewable energy, water, and climate change are urgently required in the decades to come. Caltech students, postdocs, faculty, and staff, individually and together, continue to work vigorously to expand the boundaries of present knowledge and to apply their insights for the benefit of society. Shattering boundaries is quintessential Caltech. It makes possible scientific exploits that seem impossible at first, including the rovers traversing Mars that you will hear about today. None of this is possible without our shared sense of wonder about the universe. We are knit together as a community by a shared dedication to discovery. We start the 2021-2022 academic year at a time of challenge. The pandemic has altered the personal modes of interaction that we have taken for granted for so many years. Our responsibility to protect the safety of the Caltech community and the Pasadena community at large requires changes in behavior that are absolutely necessary, but neither easy nor comfortable. Today is also a time when the fundamental mission of universities is under assault. We exist to create knowledge for the centuries and to improve the human condition today. To accomplish our mission, we need to welcome into our midst the most creative and original scholars from every background and every perspective, from every part of our society and from every country in the world. We need to let the members of our community explore and dream in an environment where facts matter, where ideas are tested and refined on the basis of their importance and impact. We need to express our views convincingly, but also be open to having our minds changed if a better idea is presented. These values have achieved expression in universities for 1,000 years, but they can be ephemeral if we do not defend them actively. Another one of my favorite New Yorker cartoons has two women standing in an interior doorway, observing a man in the adjoining room smoking a pipe, staring intently out the window. One woman explains to the other, "George is a deep thinker, but his thoughts rarely come to the surface. I know that Caltech will draw the best out of you. You will create, you will innovate, and you will build community. I wish you a safe and fulfilling year filled with discovery." It is now my pleasure to turn the podium over to a valued colleague and friend, Kevin Gilmartin, Vice President for Student Affairs.
Thank you, President Rosenbaum, for those inspiring and challenging remarks. I am Kevin Gilmartin, Professor of English at Caltech and Vice President for Student Affairs. I've been part of the Caltech community for 3 decades now, And in that time, I have never felt our resiliency and our resourcefulness so sorely tested. But it has been inspiring to see how we have come together as a community and sustained our commitment to research and education. The shared experience of coming together through a pandemic makes this convocation particularly meaningful. After more than a year of remote learning and virtual programming across so many of our usual activities, this convocation, held virtually as part of our commitment to health and safety, nevertheless marks a transition out of the virtual interruption of our campus rhythms, notably with the return of undergraduate students to campus, to the residences, and to our classrooms and labs. Convocation is always a chance for us to welcome new members of our community, along with their family and friends, and introduce them to some of what makes Caltech such an extraordinary research and learning community. This year's Convocation's theme is Mission to Mars, the future of Mars and space exploration. And it is particularly meaningful to me that you will hear from those involved in this mission at many stages in their own careers, from students and postdocs to faculty. With that in mind, it is my pleasure to welcome our keynote speaker, Professor Ken Farley. Professor Farley is the W.M. Keck Foundation Professor of Geochemistry in the Division of Geological and Planetary Sciences at Caltech, where his research has focused on the geochemistry of noble gases as applied to a range of Earth science problems, as well as the exploration of Mars and its geochemistry, geology, and geomorphology. Much of his current work uses noble gases to understand Mars history. As project scientist for the Mars 2020 mission, Professor Farley led the science team and worked with engineers to design and build the Perseverance rover, which launched in July 2020 and just over 6 months later successfully landed at Jezero Crater. The title of his talk today is Perseverance on Mars.
Hi, my name is Ken Farley. I am a professor in the GPS division at Caltech, and it's a pleasure for me to welcome you all to Caltech. I've spent my entire professional career, almost 30 years at Caltech. It's been a wonderful experience for me, and I hope it is for you as well in your years here. In addition to being a Caltech professor, I am also project scientist for the Mars 2020 mission. And in the next few minutes, I want to tell you a little bit about what the mission has been doing in our about 209 sols on the surface of Mars. That's about 6 months. And I want to tell you a little bit about my personal experience being involved in this really enormous project. I want to start with this picture. This is from a few years ago. This is a picture from up at JPL. And this is part of the literally thousands of people that have been involved in this mission. I can show you a picture of the science team. It is about equally large. So this is a really large undertaking, and it's really a great experience to be part of a big team doing a big thing. This picture was obviously taken before the pandemic. And I just want to say that when the pandemic came, this team was still scrambling to get the job done. So during the pandemic, this team drew together and managed to get the spacecraft delivered to Florida in time for last summer's launch. It successfully got the spacecraft to Mars and has been successfully operating the spacecraft on the surface the last 6 months, all through the really challenging times that we've been going through. So I want to acknowledge the tremendous effort this team has made. Could not have been done without literally thousands of people pulling together. But at a higher level, I also want to point out that efforts like these, despite all of the craziness of the last few years, big, important science and engineering undertakings are still going on. We haven't lost our ability to really do great things, despite all of the things that have been happening. And I just think it's important to keep that in mind as we go forward. There are going to be big opportunities to do great things. We haven't lost the ability to pull together and work together. I want to start with the conversation about entry, descent, and landing. This is the glory moment of this mission, when the spacecraft goes from traveling at about 4 kilometers per second through space to being at a complete standstill on the surface. This is a really tricky operation, and it happens completely autonomously. So I just want to show you a little bit about how that works. And one of the very interesting new features that the Perseverance mission had, a set of cameras that were on the spacecraft during EEL to capture what this event actually looks like for the first time. And to set this up, I want to show you something about what you're going to see from those cameras. This shows the landing site in Jezero crater. This is a crater that about 3.5 billion years ago had an enormous lake in about 40 kilometers across and hundreds of meters. And you're going to see in the image that in the video I show in a moment, this feature called the delta. So this is a place where a river flowed into this lake and deposited sediment in the slack water of the lake. So you'll see the edge of the delta about right here. You'll see this crater called Havuza, and you'll see this peculiar region here called Zeta as the spacecraft lands. And I'll start this video relatively late in the about 7-minute process of landing. So the video will begin about 2 kilometers above the surface. And the first thing you'll see is the edge of the delta, somewhat rotated from the perspective that you see here. So here we go. So there you see on the right, the delta. The spacecraft is coming in on a descent stage. So this is a powered rocket that is carrying the rover to the surface. It is looking for a rock-free region to land. And as soon as it gets close to the surface, the rover will literally be winched to the surface. So we're a few hundred meters off the surface. We will start to see the rockets kick up the dust as we are landing. So there goes the dust. And when we're about 10 meters off the surface, we begin this winching operation, which is called sky crane. And on the left, you see video that was actually captured when this was happening. So on the bottom, there goes the rover. And you can see it on its tether. It is about to touch down on the ground. As soon as it does, those cables will be cut, and the powered descent stage, which you see at the top, will be cut away, and it flies off so that it doesn't tangle up in the rover. So that is just a few seconds of this really dramatic event. And I just want to comment on everybody always likes to see the JPL engineers go crazy after the landing. This really is a fabulous moment. If you have spent a decade of your life building this incredibly complicated thing, and then you entrust it to land itself, the moment about 10 minutes later, when you learn that it has worked successfully, it is just a spectacular feeling. I was in the back room here. I got to experience this. This was definitely a life moment. Very successful landing, captured in all its glory. I encourage you to go visit the Mars 2020 website and see that full video. It's about 10 minutes long. So let me tell you about the goals of the mission. This is a rover mission, and it has 3 major goals. Seek evidence of ancient Martian life, and I'm going to explain why the word ancient is in there. Second, prepare samples for return to Earth. So the major goal of this mission is to prepare a suite of samples to be brought back to Earth to be studied with the full arsenal of laboratory equipment that exists around the world that can't be flown to another planet. And to enable the future, this is to make exploration of Mars easier with things like the Mars helicopter, which you may have heard about. But first, let me talk about this issue of looking for ancient life. Why we're looking for life at all, and why are we looking for ancient life? Well, the first point to make is, as you can sort of divine from this image of the crater floor that Perseverance took, Mars today is inhospitable to all life as we know it. There is nowhere on the surface of Mars that life as we know it could exist. It's too cold, it's too dry, and there's too much radiation in the absence of an atmosphere, substantial atmosphere. It's just not a place where anything could live. So this is not a good place to go look for extant life. But what's fascinating about Mars is when you look into its distant geologic past, more than about 3.5 billion years ago, it was very different. You might have gotten some idea of that when I showed you a picture of Jezero crater and I said it was once filled with a lake. Climate was really different in the past. And it changed about 3.5 billion years ago to the cold, dry place that we know today. So on the right-hand side here, you see an artist's conception of what Mars might have looked like at that time period. We know that there were lakes and rivers. There might have been a large northern ocean. We're not really sure exactly how long the water was present and how much there was, but the geology tells you clearly there was some. So this is 3.5 billion years ago. We're going to look for life from 3.5 billion years ago. It's useful to consider what life was like on Earth 3.5 billion years ago. And it turns out that there are very few rocks of this age. But when we look at the appropriate rocks of this age, places where life could exist, life is there, but it's very primitive. We're not seeing dinosaur bones and fish teeth. Instead, we are seeing evidence of microbial life. That's as far as life had evolved in the about 1 billion years between the formation of the planet and 3.5 billion years ago. And this picture shows an example of what microbial life looks like. So this is a rock called the stromatolite with 10 over scale. And this is what happens when microbes grow on a film of, grow on the bottom of a lake or shallow sea. They form a film that holds the sediment together and causes it to distort in this characteristic bulbous pattern. So this is the kind of thing that we are hoping to find as evidence of possible life on Mars at the same time period, 3.5 billion years ago. But I want to make just a very direct analogy. So you see here what Jezero crater looks like today. Gold and it's dry. But that delta that you see here provides really clear evidence that it once looked more like this. Artist's conception of a 40-kilometer diameter lake, hundreds of meters deep. 40 kilometers diameter is a really big lake. And so the direct analogy that I would make is this is what Mars, in this particular spot, may have looked like at the same time period that I showed you evidence of life on Earth. Two different planets. We have a shallow lakes and seas on Earth. There's evidence of life. We have a lake here on Mars at the same time period. It becomes a very reasonable question then to ask, if there was life on Earth, why wouldn't there be life on Mars? So that's one of the motivations for actually going there and looking to see if there is any evidence that life existed at that time on another planet. Now let me tell you a little bit about what we've done. We've done a lot in our several hundred days on Mars, and I can't go through much of the details here. We've driven about 2.5 kilometers along the edge of this feature called Zeta. And I want to show you the one big moment for me, or the biggest moment for me, which actually just happened in the last few days. And that is the successful collection of our first sample. So I told you one of the major goals of this mission is the collection of a suite of samples that can be brought back to Earth by a future mission. And this is it's a very difficult thing to do, to collect samples. This is a very sophisticated robotic system, the most sophisticated robot that has ever been flown to make this work. And our first attempt, which happened about 3 weeks ago, the robotic system worked flawlessly, but we recovered no rock. The rock basically fell apart and slipped out of the sample collection system. So we were quite disheartened by that. And then just a few days ago, we tried again, and we were successful. So let me step you through this. In the upper panel here, you see the target. So this is a series of rocks that are part of a layer that is slowly degrading. So this might have once been a lava flow, and all these rocks are part of it. We decided that we would collect this rock here, which is about the size of a briefcase. We drove up to this rock and we pulled out the microscopic camera to look at the surface of the rock. What we have found so far is that the rocks in our exploration area are all covered with stuff. So there's dust, and there's a kind of a peculiar grayish and purplish coating, which means we can't see what's inside the rocks. Geologists and geochemists really want to see what's inside the rock to learn what that rock is made out of. They can't see it through this coating. So we pulled out our abrasion tool That's shown in this image here. This is on the robotic arm. This is a rotary percussive drill that has this bit on it that we push out onto the surface of the rock and force into the rock to make a patch that is about 4 centimeters across and about 1 centimeter deep. And when we pull back, we see, wow, this is spectacular. We can see lots of things inside this rock. We can see crystals. This reddish stuff is iron oxide. This looks like it could be a basalt that has seen interaction with water. Maybe that's groundwater that was associated with the lake. So this was really interesting for us as something to collect. So based on what we saw on the abrasion patch, we decided we wanted to try to collect this sample. So we took a sample tube. Each sample lives in its own tube. This is about 10 centimeters long. We took the sample tube and we put it inside the drill bit. This is a coring drill bit you can see spinning here. It's also mounted on the robotic arm. And we extended this assembly out onto the rock and we bored a hole in it. And when we pulled back and took a picture down the bore of the tube, you can see right here, a little bit of detail here. We successfully captured this sample. We transferred it into the rover and we sealed it and we put it in storage. This big moment, we were a lot of cheering. It wasn't quite like entry, descent, and landing, but there was a lot of cheering when we had this first sample in the bag. And we then immediately went and took a second one. That's why there are 2 bore holes here. So now we have 2 samples in our about 30 samples that we need to collect. We have 2 samples already prepared and ready to go for return to Earth. And let me conclude by telling you a little bit about how this process is going to work to bring these samples back. The Mars 2020 mission is not responsible for bringing the samples back. That would be too complicated for us to do all of the science we need to do, driving around and identifying and collecting rocks, to also have a rocket with us. So instead, this Mars sample return campaign involves 3 missions, which are jointly being developed by NASA and the European Space Agency. There's the Mars 2020 Perseverance mission, and later in this decade, samples will be transferred to the first of the follow-on missions, which is a lander with a rocket. So the sample tubes, about 30 of them, will be transferred into a sphere we call the orbiting sample, the OS, which is put into the rocket. And that OS is launched into orbit, where it then gets captured by a third mission, an orbiter, which then ferries the samples back to Earth. If all goes according to plan, these samples will be back on Earth in 2031. Of course, that's still a decade away, but I'll just point out that we started development of the Mars 2020 mission about a decade ago. So we are about halfway there. When these samples come back, they will be studied for all sorts of things that include determining the ages of the rocks. When was that lake actually present? What was the climate like at that time? And in addition, these samples will be analyzed for evidence of life on another planet. This will be the first time that scientists have ever been faced with that question. How do you look for life that is potentially different from the life we know here on Earth? I think this is going to be a really exciting time when scientists need to dig in and actually think about how you would do that. What would you really look for? So hopefully in the next decade, the community will be doing that. And I just want to say, I think this is going to be an exciting time. So especially for the students that are just starting out, there are going to be a lot of opportunities in different kinds of disciplines to contribute to this effort. In the engineering over the next decade, and also in the analysis of the samples in the geoscience community, and also in the biology. So it's a really exciting time. And I will conclude here, and you will hear from several other members of the Caltech community who are also involved in this mission. Thanks for your attention.
Hi everyone, my name is Himani. I'm a graduate student with Woody Fisher in the Geological and Planetary Sciences department here. Welcome to Caltech. A little bit about me. I grew up completely mesmerized by the universe in this one amazing place on Earth called NASA that held press conferences about the secrets of the universe, and it was the only place I've ever cared to work. For proof, I have this very embarrassing picture of me as a 6-year-old with a NASA astronaut at Kennedy Space Center. To build something that left the Earth seemed like the coolest job in the world, and so I did my undergrad in aerospace engineering. And my senior year, however, I got to do a project that really pivoted my path. Thanks to my advisor, Tellis Onstott, I was able to test some bacterial samples on the Mars 2020 rover instrument called Sherlock up here at JPL. And this project was amazingly interdisciplinary: the biology of the samples, the chemistry of the Raman detections, the physics of the spectroscopy, and the geology of the Mars analog we were trying to simulate. And I realized what I cared about, what I had always cared about, which was the fascinating interconnected science that we got to learn from these missions. So if I had to give you one piece of advice, I would say don't be afraid to explore as many research opportunities as it takes for you to be out of this world excited about your work. I applied to Caltech because it is the center of students and faculty working on planetary missions, as you can see here today, but also because the data from the rover is only as well understood as we can compare and contrast it to the geology on Earth. And Caltech is exceedingly equipped for the exchange of discoveries between lab research and mission operations, which makes it a really special and exciting place to me. These days, I get to operate the SuperCam instrument of the rover, as you can see here, which shoots lasers on Mars up to 7 meters away and has a variety of spectroscopy techniques that help reveal the chemical compositions and mineralogy of rocks in Jezero. And Jezero has thrown us a few beautiful surprises. This is Kodiak, a little isolated mound of rocks with some beautiful layered beds and dipping beds, and it actually shows us evidence of Mars having a lot of water in the past. This is an image of a rock known as Guillaume, which was abraded by a tool on the rover. And what you're seeing here is actual mineral crystals, something we've never gotten to see on Mars before. And this is not a rock, but a dust devil. I'm just amazed that we are able to capture these storms with our cameras. My favorite moments on the team are when we have our weekly meetings with Caltech professors and students of the team, and the 10 of us get to spend a Friday ruminating on the nature of early Mars, like I imagine scholars in the 16th century did, but instead of apples falling on our heads, John Grotzinger annotates sedimentary beds on Zoom, and we all squint at an image to try and find sulfate crystals where there may not be any. It's a privilege to squint at sulfate crystals with professors like Woody and Ken and Bethany and John, who are just so enthusiastic about squinting and inspiring in their span of knowledge. What's most interesting to me in all of this is decoding the history and origin of life. And, depending on the day, we feel closer or further to finding life on Mars. But that's the fun of it, the fun of research and science and PhDs, at least in my very new eyes. You never know what's going to happen at work tomorrow, and not in the bad way, like stock market analysis at an investment bank. And yeah, sometimes your data makes no sense, or the detector betrays you, or the rocks lie to you, and it's disheartening. But then I just remind myself that I'm looking at the image of a crack in a rock taken by a robot that is 245 million miles away, and it makes all the disappointment worth it. And sometimes, really, the most important thing you can do is get out of lab and get to know all the amazing people around you by sitting at a random dinner table in the cafeteria. Having people to eat large amounts of ice cream with is essential to getting through Caltech, I promise you. As for the future of space exploration, I can't wait for Mars sample return. The kids will have it too easy, no more squinting at crystals. I'm so excited to witness the first two-way interaction with another planet and experience the next distance revolution with my own eyes, something of how I imagine the early 20th century felt to people when you could now get to new corners of the planet in hours. But this rover is just the start. One day there will be eel-shaped robots diving into the vents of Enceladus and submarines in the oceans of Europa, and the days of the dune buggy will be succeeded by the vehicles of Jules Verne's dreams. And I can't wait. On that note, I'll say goodbye and wish you a wonderful journey at Caltech, and thanks for listening.
Hi, my name is Eva. I'm a PhD student within the Division of Geological and Planetary Sciences at Caltech, and I also work on the Perseverance rover science team. I actually initially came to Caltech when I was 20 years old, and I was doing a study abroad program at Caltech from my undergrad institution back in Denmark. And I was really interested in studying other planets. I was really interested in the planetary processes that control the climates of planets and controls the ability of a planet to harbor life. And I was really blown away by all the cool research that the researchers were doing, working with these different space missions at NASA. And so I eventually decided to move from Denmark all the way to America to do a PhD program here at Caltech. I actually started out working with the Mars Reconnaissance Orbiter, which is a satellite that orbits around Mars. And I was studying the landing site of the Perseverance rover with this satellite. At that time, we actually had multiple candidates for landing sites for the Perseverance rover. So I got to go to all these meetings and workshops in which I could share my science, studying the landing site of Perseverance, and listen to all these other scientists tell about their findings at the different landing site candidates. And I even got to cast my vote for which landing site that I preferred. And I was really happy that we ended up with Jezero Crater. So one thing that you may not know is that before Perseverance lands, hundreds of scientists and engineers work to pre-plan all the possible driving routes, all these science questions, goals, experiments, and samples that the Perseverance rover is going to achieve and take. So this is just one product showing, all these different games we play, trying to make out different routes that the rover could take. And so it was a big part of that planning, and it was really cool to be a part of. And one really funny thing was that we actually made a geological map that's shown here for the Perseverance landing site before it landed. And we had all signed up to map each of these little quadrants here. And kind of randomly, I had signed up to map the quadrant that Perseverance eventually landed in. So my little map, I got to see in all kinds of news, media, and so on. And that was just a really fun and amazing experience. So when the Perseverance rover landed, I am part of the scientists and engineers that show up to work every day, and they analyze the new data that has been retrieved by the rover. And then they bring that data to relevant scientists and engineers, and then you help plan what the rover is going to be doing in the next few days. I started out doing this kind of work on the Mastcam-C camera, which is this camera in the head of the rover that brings you all of the amazing imagery that you have maybe seen from Perseverance. Within the first few days of working on the Perseverance rover, I participated in the team that brought you some of the first images, like the first panorama and these images shown here that you may have seen before. I still continue my work on the Mastcam-C camera, but I actually also spend a lot of time working on the Sherlock spectrometer, which is in the arm of the rover. You may have heard about the science goals of the Perseverance rover. It's basically to understand whether there's possibility for life on Mars in studying the geological history of Mars, studying whether there's what we call biosignatures on Mars, and then sampling these materials to eventually return to Earth. And Sherlock is actually really important in addressing these different science goals because Sherlock is a Raman spectrometer. And a Raman spectrometer works by shooting a laser at the surface of Mars, and then that allows you to understand what kinds of molecular bondings are on the surface of Mars. So not only does that allow you to characterize the materials that are there, it also allows you to look for organics, our building blocks for life. And so Sherlock actually addresses a lot of these science goals in different ways. So looking towards the future, what am I the most excited about? I'm probably the most excited about the sample return program. Aside from working with satellites and rovers, actually also do a lot of laboratory work. And I would really love to be able to hold one of these returned Martian samples and perform some of the analytical techniques that can really only be performed in a big laboratory here on Earth. That would be such an awesome and sort of culmination of my career if I would be able to do that. So I'm super excited about that. Aside from our Mars missions, we actually also have a lot of really interesting missions that I'm looking forward to seeing going to different planetary bodies out of NASA, many of which have ties to JPL and Caltech. So in particular, I'm very excited about these new missions going to Venus, our satellite that's going to Jupiter's moon Europa, this Dragonfly mission that's going to Saturn's moon Titan, and then all these amazing new missions going back to the moon. And so with that, I just want to say that no matter what kind of discipline you're working in, if you are really interested in space missions, there's so many opportunities for you to work with these NASA teams here at Caltech.
Hi, I'm Nathan Stein. I'm a former grad student and a postdoc at Caltech in the Division of Geological and Planetary Science. And I want to spend a little bit of time today just talking about my journey at Caltech and how I came to be involved in the Mars 2020 mission. So my first experience at Caltech, or at least in the Caltech environment, was way back in 2014 when I was a summer intern at JPL. And back then I was working on the Curiosity rover, which is another rover that was developed by JPL and is actually still operating on Mars nearly a decade after it landed. And this is a picture of me in the JPL Mars yard, which everyone at Caltech should spend time visiting at some point when they're there. And back during that summer, I was working on some mobility tests in the JPL Mars yard, trying to figure out how the rover interacted with the terrain and how we could do a better job of navigating the rover and preventing damage to the rover's wheels. So I joined Caltech a year later as a grad student in planetary science, working with Professor John Grotzinger on the Curiosity mission. And I remember during one of the first chats I had with John Grotzinger, he told me, working on Mars is great, but you got to do something else to keep yourself grounded. You got to work on Earth as well. And this was kind of my first foray into something that I really like about Caltech, which is the opportunity to work on a whole lot of interesting projects, whether they're on Mars or something a little bit closer to home, with a whole lot of interesting folks. And so in addition to the work that I did with Curiosity, I also worked with another Caltech professor, Professor Bethany Ellman, on NASA's Dawn mission, which was a mission that went to a couple of asteroids, Vesta and Ceres, and did quite a bit of work building and flying drones down in the Turks and Caicos. And this was a collaboration with Caltech Center for Autonomous Systems and Technologies. So all fun projects, some of them more tenuously related to Mars than others. Most of the work that made up my PhD at Caltech was with Curiosity, which is the rover that you see here in a pretty recent selfie. This is a location in an ancient crater on Mars called Mont Mercou. And the objectives of Curiosity were in many ways similar to some of the objectives of the 2020 mission, which is to analyze this past habitable environment on Mars, this crater called Gale Crater, to understand the ways that life may have been able to develop on Mars in the distant past. After my work on Curiosity, toward the end of my PhD and into the beginning as a postdoc, I had the opportunity to start working with the Mars 2020 rover and a particular instrument on Mars 2020 called Mastcam-Z. Mastcam-Z is arguably the most advanced camera to ever land on another planet. And it really forms the eyes of the rover in many ways. And there are a few major utilities here. One is just performing the function of letting the rover be able to see where it's going and what it's doing, both for navigation and for contextualizing observations on the surface. And obviously, both of those are super crucial for a mobile science platform like Perseverance. Another that's pretty central to the science that we do at Caltech is that the images form the opportunity for us to contextualize and understand geology. And as you've heard, one of the main objectives of the Mars 2020 mission is to find signs of past habitability in this ancient crater called Jezero, where there's ample evidence of a long history of flowing water in the distant past. So I won't go into technical details on any of the results from the mission so far, but I do want to share just a couple of my favorite images from the mission so far with you. The first is an image taken by Mastcam-Z a couple of months into the mission. So this is an image from Jezero crater of a putative delta remnant. This is probably left over from a delta that once filled much of the crater, deposited by flowing water billions of years ago. And you can see in this image confirmation of what we thought was there based on images taken from orbit over the last couple decades. In this image, you can see the subtle signs of cross-bedding, the kinds of signs that a geologist would see as a very clear signature of flowing water if they were looking at a similar outcrop on Earth. And what's really exciting about this image and about the capabilities of Mars 2020 is that these kinds of delta deposits, especially at the basal or distal deposits of a delta in Jezero, we think that's where organics are likely to be concentrated. And these kinds of deposits, either the ones that you see in the image or deposits that are fairly close by, will certainly be a target for sampling by 2020 as the mission progresses. There's one other set of images that I think is just too cool not to discuss. And this kind of goes full circle with some of the work that I did at Caltech over the last few years working on drones, which is that in addition to all of the amazing science that Perseverance is enabling, Perseverance also provided the opportunity, the Mars 2020 mission provided the opportunity to fly a drone. And you can see on the left here, a selfie that Perseverance has taken with a drone called Ingenuity. And on the right is this grainy but incredible photo taken by Ingenuity in flight, where you can see Perseverance likely in the act of recording the flight as that image was taken. So just to leave off with a couple of words about the future of Mars exploration in planetary science at Caltech. I remember when I first joined Caltech, I had some apprehension because I was coming a few years after the start of the Curiosity rover mission, which had landed back in 2012. I was joining back in 2015. And the concern on my end was that in some way the ship had kind of sailed and that the most groundbreaking science had already been done. But I don't think that ended up being an issue at all. In fact, I think I joined Caltech at a great time and was able to contribute in a lot of fantastic ways to that mission and learn a lot from an amazing science team, both at Caltech and in the broader scientific community. The way that the Mars 2020 mission is set up kind of puts it at a juncture between a couple of decades of work that have culminated in this amazing technological feat to get this rover to the surface, and what is sure to be a period of even more amazing discoveries in the future. This includes the potential for sample return, and like all planetary missions that have preceded it, Perseverance will answer a lot of exciting questions, and it's sure to raise many more. And so I think this is the perfect time to be joining Caltech, whether you're working on Mars or a problem closer to home. And I wish everyone the best of luck going forward, wherever their endeavors take them.
Hello, students, faculty, family, and friends. It's an honor to be speaking with you today. My name is Katie Stack Morgan, and I'm a research scientist at the Jet Propulsion Laboratory and the Deputy Project Scientist of the Mars 2020 Perseverance Rover mission. I'm thrilled to help kick off what I hope is an exceptional year, and for many of you, the beginning of your Caltech journeys. I began my own journey at Caltech in 2008 as a first-year graduate student in the Division of Geological and Planetary Sciences. I was sitting where you are now, though in my case, fresh off from my first visit to the Venice Boardwalk and still gawking at just about every palm tree I came across. But as I filed into Beckman Auditorium for Convocation 13 years ago and looked up at those twinkling lights on the ceiling, I could tell that this was going to be a moment that I looked back on and said, this is where it all started. During my first semester at Caltech, the Mars Science Laboratory Curiosity rover was in the midst of a big push-up to meet its original launch date in 2009. My advisor, John Grotzinger, who was the project scientist of Curiosity at the time, invited all of us up to the high bay at JPL for a look at the rover as it was being built. I didn't really know much about the mission at the time as a first-year student, and I mostly remember thinking that the rover had a lot more parts to it than I had expected, and that JPL seemed like a pretty intimidating place. But a few months later, we found out that the Curiosity launch had been delayed to 2011. Although we were all pretty disappointed at the time, as it turns out, I think that those extra years made all the difference for me and my path to where I'm sitting today, which, if I had to sum it up, would involve a little bit of luck, some fortuitous timing, and a total all-consuming passion for doing science with Mars rovers that surprised even myself. But that passion definitely wasn't always there. I whiled away those first few years of my time at Caltech, feeling the way that I think many grad students do, scrambling to come up with manuscript-worthy research projects, feeling generally pretty insecure about my science, and thinking way too much about how to solve my two-body problem. I had also started to put out some feelers to industry employers thinking that research and the academic path just might not be for me. But 5 months before Curiosity landed on Mars in 2012, I suddenly found myself on the rover team as a fourth-year senior graduate student with a front row seat to the inner workings of a Mars rover mission, and I loved every minute of it. I threw myself into making maps of Curiosity's landing site with orbiter images, trying to understand the geologic context of the rover's field area at a scale that no one ever had before. And once the rover landed, I took full advantage of the very flexible schedule that grad students and really most Caltech students are known for, and worked anytime and all the time to be the first person on the team to look at and interpret the new images that streamed down from the rover. I also found myself a niche, realizing that I was one of a few team members who was interested and able to move easily back and forth between the rover scale and the orbiter scale, and that so much of our strategic science planning for the rover relied on exactly that comparison. I also realized that I loved the challenge of rover operations. There are new problems to solve every day as we ask ourselves how to bring together a team of scientists and engineers with different priorities and diverse interests to operate a single robotic spacecraft on Mars. I was hooked, and never before has anything I've done felt quite so right. Now, I know that not everyone has that aha moment where you find yourself in the middle of the Venn diagram of things you're interested in, things you're good at, and things that people will actually pay you to do. But I consider myself so incredibly fortunate that I did find myself there, and I know that I have Caltech and the opportunities it presented to thank for that. When I transitioned to JPL as a full-time research scientist, I had the opportunity to orchestrate Curiosity's 6-month-long campaign at a place called Pahrump Hills. I spent my days at JPL moving back and forth between the science room and the engineering room, prioritizing science objectives for the rover and finding the best way to communicate between these two groups that don't always speak the same language. Then I'd come home at night to pore over the new data to figure out what and how these sedimentary rocks in Gale Crater were deposited. One of my favorite images from the MSL mission is this selfie that Curiosity took while at Pahrump Hills. After years of working on Mars rovers, you kind of get used to doing geology by robotic proxy, but never before have I felt quite so in sync with a robot as I did during this campaign. And when I thought every day about what the surface of Mars looked like through the rover's eyes, envisioning that I was standing on the surface of Mars, seeing and observing these rocks myself. Seeing the sausage being made in real time and having a hand in making it myself helped me feel a little less intimidated by JPL and a little more like I was where I belonged and deserved to be. My time working on Curiosity turned out to be a pretty good preparation when Mars 2020, NASA's newest rover and the first leg of Mars sample return, was on the hunt for a new deputy project scientist. Although my previous rover experience has certainly come in handy, Mars 2020, with its unique challenges and ambitious mission objectives, has also forced me to step outside my own experience and flex and adapt in ways I never thought I could. But honestly, trying to get 500 plus scientists on the same page while also keeping a rover operating on the surface of Mars really doesn't leave you with much choice. But we're now 7 months into the Perseverance's rover's mission on the surface of Mars, and by all accounts, it's been an astounding success. Just a few weeks ago, Perseverance acquired its first rock sample, marking the real beginning of Mars sample return effort. It's exciting to think that some of you may be amongst the first scientists to study these samples, and that others of you may end up designing, building, and operating the missions that will bring these samples home. My life these days looks pretty different than it did when I was a grad student working on Curiosity. I've got 2 young kids, and while I'm sometimes still up at odd hours of the night, it's not usually by choice, and more often because there just aren't enough hours in the Earth or Mars day to get it all done. But I'm thrilled that there's a place in the Mars community and at JPL for someone like me to take on a leadership role in an endeavor on the scale of Mars sample return. And at the end of the day, sometimes quite literally, it's images like this one taken by Perseverance at Jezero Crater of the Kodiak Delta remnant, an outcrop of what was once an extensive ancient delta that reminds me that there is still so much to learn about planets beyond our own, even if they look kind of similar to the way our planet used to look. In the case of Mars, we can read its rock record and use individual layers, their shapes and thicknesses, whether they're coarse or fine-grained, and what they're made of that may hold the key to some of the most fundamental questions about life in the solar system and the evolution of planets through time. So if there's something to be gleaned from my journey, it's that while each of you will have your own unique experience to create here at Caltech, it's that your time, like mine, will be filled with opportunities. Some that you'll take and some that you pass by, lulls where you wonder what you're doing and what it's all for, and times when everything just clicks and you realize that these successes, however small or personal they may be, are why we show up day in, day out, and sometimes at very odd hours and while living on Mars time. Thanks so much for your time, and I wish you all the best of luck in the coming year and many aha moments in your future.
I came to Caltech for multiple reasons. The most pertinent of them is just the collaborative nature and the strong sense of identity, and most important to me is the research-based education.
I'd felt a yearning, one might say, always to come back to Caltech after graduating. There was something very special about Caltech, which was a really true and passionate love of science that I felt here. This is really not just uncommon, but non-existent anywhere else.
So I'm particularly interested in self-propelled nanoparticles. So I use computer simulation to really understand how these things work. There's a potential that you're the first person to really look at this behavior, and being like the person who's actually pushing the boundary forward is kind of why I get up in the morning.
What LIGO has done is to open up for the first time an ability to see this aspect of the universe that lives side by side with stars and planets, and yet has never been seen before. It gives humans for the first time the possibility to learn about the warp side of the universe.
So my research is in computational biology. It's not just that we do experiments and then go and analyze the data. The computer science is developing the technology and the experiments, and they can be used to better understand the molecular biology of the cell, and also developing diagnostics for health applications.
I combine quantum information theory with thermodynamics. This combination informs our basic fundamental understanding of the flow of time, how efficiently we can process information, and other fundamental ideas.
Caltech is changing the world in a number of different ways. One is just the cutting edge research, which leads to new technologies. But I think also the students that come out of Caltech too. These students go other places and take what they've learned here, and they're able to share that knowledge.
Caltech does train the next scientist. I think it's really cool to be part of that group.
I feel like every time I turn around, I see someone who has invented a new field. It makes me want to strive to make the quality of my work not just very good, but extraordinary.
I want to close by thanking everyone involved in this Convocation program for the time and energy they put into welcoming new members of our community and celebrating the start of this singular academic year. I particularly want to thank those of you who worked behind the scenes in programming and production. Michelle Rodriguez in the Vice President for Student Affairs Office, Ed Brown in Strategic Communications, and in Academic and Media Technologies, Leslie Maxfield, Gina Marie Napolitan, and Gina Chen. Well done, everyone. And finally, for all the new members of our community and their families and friends, welcome to Caltech. We're thrilled to have you join us.